The next section will be on water and energy, and in this section we'll have two presentations, and we'll start with the first presentation by Debelina here from Texas A&M. So first on the screen, maybe.
Hello, Debelina.
Hi, Rabia and everyone. Thank you for the opportunity to present this research. So this kind of brings in the perspective of systems, as you mentioned in the previous section. So what our work was, this work was done by Bhojwani with his master's thesis, Kevin Topolski, Rajiv Mukherjee, and myself and Dr. El-Halwagi. And the topic of the work was technology review and data analysis for cost assessment of water treatment systems. So basically what this work entails is we were looking at a body of review literature that will aid in the development of water networks that would connect supply chain, reuse, and recycle of water systems. So basically, when you talk about the systems approach, what you are faced with is you have the supply chain of the water systems, and we have to either reuse and recycle the water, but we need to have data that would aid in the development of such a system of water networks. So that was the main objective of this study, to get the data for this superstructure that we created. So we worked with capital, operating, and unit product cost comparison for water treatment technologies. We looked at cost and other technical data compiled from over 100 research articles, white papers, and technical reports. The network representation of water distribution and treatment, followed by reuse options. So we also created what we were looking at the network, and a brief overview of integration of coupling strategies that can lower cost for treatment. So we didn't go into the details, that's coming up in a second paper, but we briefly created a structure where we could use one single integration method, or we could couple strategies that would lower the cost for the treatment. This also paved the way for the formation of optimization frameworks for macroscopic water network systems, for example, cities, regions, devices. Okay, so this the chart on the left shows a high-level hierarchical structure of flowchart for decision-making process. So if you look closer into it, this was for the choice of a suitable technology and a pathway for treatment of the water. So we started with wastewater characterization. So we needed to know what a wastewater is. And we had then we put it through certain different methods for pre-treatment of the wastewater, then removal of organics, and finally we went up to removal of salt content, the TDS content. So some of the selection processes, the selection of the process depended on feed water quality, the salinity, hardness, pH, BOD, etc. The capacity or the quantity of the water that we are treating, the desired product quality, the energy availability, the site location, and environmental conditions. So I'm going to briefly describe that in the next slide. So the methods for water treatment that we chose were the data collection. So this included the data collection for different treatment technologies. That was done on the basis of the type of the technology. So we used multi-stage flash, multi-effect distillation, thermal membrane distillation, vapor compression, reverse osmosis, ultrafiltration, nanofiltration, etc. Then the second one was cost, capital cost versus capacity, operating costs, energy, chemicals, labor, membrane costs, and maintenance costs. Energy, the unit electricity used and the thermal energy consumption, the performance, the output ratios, the performance ratios of the different stages, the conversion factors, the maximum feedstock salinity, and output quality. The cost correlations were developed using regression to find relation between capital cost, operating cost, and the capacity of the treatment plant. These are some of the results. So we have the capital cost capacity correlations developed from, and as I said, this was done from over 100 publications on cost data. Then we have the unit product cost versus capacity. So the detailed breakdown of unit and operating cost heads for each capacity range. Done membrane techniques for more suitable than thermal due to lower cost. The thermal technology is suitable for areas with waste heat availability, dual purpose plants. So these were some of the key results that we got from this research. And finally, in the key messages, we created the source interceptor sink diagram where we had groundwater source aquifers, the surface water sources, the reused water, and then they go through this use phase of municipal manufacturing irrigation. And stream mining and produced water. And then we have this interceptor network where we use the water that has been the waste water from these processes, and we use this water interceptor network to treat them as.
Please, not the speaker. If you are not the speaker, please mute your phone.
All right, so this is the final network diagram that we have created from this, where we are having these sources on the left from where wastewater is created. We then have the water interceptor network. It is kind of a superstructure design where we bring in all the technologies possible. And we can add to this if any new technology is being introduced, we can add to that. But this is what we have as of now, the pre-treatment, the primary, the secondary clarifiers, and then we have the tertiary, primary treatment, secondary treatment, and tertiary treatment. And then we get this water out at certain qualities which will be available for reuse in the same sectors that we had got those wastewater from. So with that, I would like to conclude, and if there are any questions, I would like to
Thank you, Evelina. We'll move to the other water energy presentation, but before we do that, I'll mute everyone again and give the floor to Ahmed Mroue, who will be giving the next presentation in the water energy team. Go ahead.
Hello, Basil. Can you hear me?
Yes.
Okay, so good afternoon to Lebanon. Good morning to the U.S. Good afternoon, Dr. Rabia. The paper I'm about to present is titled the Energy Portfolio Assessment Tool, EPAT, Sustainable Energy Planning Using the WEF NEXUS Approach. Texas case. The authors are myself, Dr. Rabia, Dr. Pistikopoulos, and Dr. Holtzapple. Let's jump directly to the background and objective of the paper. As for the background, energy policies driving the sustainable energy transition is often disregarding the outcome trade-offs that are drawn from the interlinkages between energy and natural resource systems, such as water, air, and land, which in many cases is leading to unintended consequences, which is what we'll see later on in this presentation. Basically, the theme of this whole webinar is to stress on Nexus awareness and Nexus holistic frameworks that can help policymakers bridge this technical and knowledge gap in policymaking for us to ensure a long-term sustainability for not only the energy system, but also the connected natural resource system. Which takes us to the objectives of this paper. The first is to develop a tool to assess the sustainability of energy portfolios through the quantification of energy policy trade-offs across water, environment, land, and economics. Second objective is to assess the current and projected energy portfolios of Texas using the developed tool EPAT. So, covering the objectives and the background, moving to the methods. So, what is EPAT and what does it do? EPAT is basically a scenario-based tool that quantifies the trade-offs of energy portfolios. In other words, it kind of mirrors the end results of policies, which allows the policymaker to have the chance to evaluate the sustainability of an energy policy, both environmentally and economically. Looking at the figure in the slide, looking at the tool framework, the input is the energy portfolio, which consists of two main segments: energy production and electricity generation. The user has the chance to, or EPAT allows the user to customize the energy scenario for production and for generation, and has the chance to choose the production technique for oil, gas, and coal. Also, to assign the water use percentage. As for the power generation, the user is able to identify the technology used in generation for natural gas, for coal, for solar systems, wind, hydro, etc. Yes. So, and the outcomes or the output is in four main quantitative parameters. Basil, can you move back to the slide, please? Yes. The output is in four main quantitative parameters: water, emissions, land, and cost, revenue for generation and production, respectively. So now moving to the results. In this paper, we assessed the current and the 2030 energy portfolios of Texas. All projections are from the EIA, and we ended up with three scenarios. The first one is the base case reference scenario, which describes the status quo. The second scenario represents the Clean Power Plan, which is a policy currently enacted or soon to be removed, a policy to mitigate carbon emissions in power generation, and also the scenario includes a strong water use policy in energy production. The third scenario is a scenario which depicts the absence of the Clean Power Plan and also a weak water use policy in energy production. Time does not permit to give a go back please, Basil. Yes, time to give a kind of a description of the scenarios in terms of technologies used and in terms of production techniques used. So I'll jump directly to the results. In the results, this trade-off analysis chart is basically what the stakeholder and decision makers are missing. EPAT quantifies the trade-offs of policies and shows the stakeholder the respective positive and negative impacts of an energy portfolio change. So looking at the second scenario, the Clean Power Plan succeeded in mitigating carbon emissions in power generation, as the emissions remained flat through the 18% increase in generation capacity in 12 years. Another positive result is that water consumption, due to this Clean Power Policy Plan, decreased by 6% just from raising the water use percentage from the average 20% to 30%. Nevertheless, which are the unintended consequences, we obtained some negative trade-offs. Carbon emissions of energy production increased by 35% by the year 2030. Also, due to the massive renewable energy deployment in scenario 2, land use increased by 143%. So the third scenario, which is the absence of the CPP and also a weak water reuse policy plan, we clearly see that in the absence of the CPP, emissions in power generation increases by 20%. And so will water consumption increase as well due to the technology adoption. A weak water use policy leads to a 13% increase in water consumption for energy production. What is worth pointing out is that with and without the CPP, the total average cost of power for the end user increases by the same magnitude, which is 18%, which means that a conservative scenario moving towards a more sustainable future costs the same as an unsustainable energy portfolio from the end user point of view. So the key remarks of this paper is that policymakers and decision makers can benefit from a Nexus holistic framework in energy policy development. And EPAT is a tool that enables the policymaker to quantify the outcomes of a policy or an energy scenario and then evaluate the sustainability of the trade-offs, both environmentally and economically. We have learned that the conservation policies, in this case the Clean Power Plan, sometimes have some unintended consequences, unintended negative trade-offs. Finally, sustainable energy development requires a move away from the silo approaches to a more comprehensive Nexus methodology. And that was it. Thank you.
Thank you, Ahmed and Evelina. And I think with this, we'll move to the third Q&A session.
Thank you, Ahmed, and thank you, Evelina. Any questions from AUB crowd?
Any questions from you?
We have a question. Just a second.
Thanks. The question is a bit controversial. It's actually from the marine side and the marine perspective of the Nexus and all the desalination. We've heard desalination in the previous 3 or 4 presentations. Okay, we're trying to find this synergy and symbiosis between water, energy, and food and everything. But what are we doing with all the chemicals that we use in the desalination? Because the seawater is not just salt. To stop the salt, we need a lot of chemicals, and then what do we do with the brine at the end? Everybody was just calculating the cost versus the fossil fuel. We're not dealing about this. So we leave this for another 30 years when we have a bigger problem, either when we dump the 3 or 4 kilometers deep in the soil, or when we throw them back in the sea, and then, oh, we remember. So that's my question.
Thank you. Evelina, would you volunteer to respond?
Evelina had to leave the room, so she is not available.
I'll try to attempt to answer the question. A very important one. There is an echo. I'm not sure. The echo is still there. I don't know where is it coming from. Somebody logged in twice, or. But anyway, there are technologies with the zero discharge that are out there. They're a little bit more expensive. So the question is society willing to pay for that, and who's going to pay for it? I think we need to engage the stakeholders, and I 100% agree with you, is that most of the countries who rely heavily on desalination have some of the highest water per capita usage. So there has to be a balance between input and output, between supply and demand, but environmental impact is a huge deal that we need to be dealing with. And but again, the other side of the coin is some economies cannot exist except on a desalination water. Unfortunately, in Lebanon here, many of the new development have desalination, but there is no regulation to deal with the environmental impact. There has to be, and there has to be brine management embedded in the cost of desalination that we have to look into. So I cannot agree more. Back to you, Basil. Any questions from Texas?
Do we have any questions here? Maybe I have a question to Ahmed, a quick one maybe. What would it take to replicate the Texas case study with the tool elsewhere?
Well, can you hear me, Basil?
Yes.
Okay. Tool is very flexible, and it allows the user to, every state and every country has a unique energy portfolio in terms of production and in terms of power generation. And the tool allows the user to model these various portfolios within by choosing the technologies and the techniques of the production and generation. So what it takes is that currently this EPAT has all the techniques and technologies for Texas, but it is very easily capable of being expanded to include more power generation technologies and cooling systems that are used in other geographic regions outside Texas, also in terms of production.
Thank you, Ahmed. It seems we also have another question from the web, from Corinus, and he's asking Ahmed on his results why the carbon emission on scenario with and without CPP on 2030 will increase by the same 35%.
Okay, so in scenario 2 and scenario 3, in terms of energy production, and time did not allow me to elaborate more on the scenarios used. So in scenario 2 and scenario 3, EIA had a reference projection in terms of energy production. So scenario 2 and scenario 3 had the same energy production portfolio, therefore the same amount of natural gas to be produced in scenario 2 and scenario 3, also same amount of oil, same amount of coal. But what differs in energy production between scenario 2 and scenario 3 is that we have two different water policies. So the only variable between scenario 2 and scenario 3 in terms of energy production is the water consumption and water withdrawal. So that is why the carbon emissions in scenario 2 and scenario 3 is the same. The CPP is directly enforced on the power generation. So this is why you can see that CPP succeeded in mitigating the carbon emissions in power generation, whereas the increase in natural gas being used in power generation has led to an increase in natural gas production, which leads to to more carbon emissions from energy production.
Thank you, Ahmed. Thank you. I think with this we finish the water energy section and move to